Okay, 2.1 relations and functions. This comes from chapter 2, which is linear relations and functions. And there is a lot of information in this particular section, a lot of vocabulary. It all ties together, but let's take a peek here. Cartesian coordinate plane. This is a picture of a Cartesian coordinate plane. It's named after this guy, Rene Descartes. I'll give you a sticker if you remind me in class to tell you the quick little story, and I'll try to make it quick, about Rene Descartes and how this Cartesian coordinate plane came to be. By the way, that's where it comes from. Okay, quadrants. I'm just going to tell you. 1. This is quadrant 2. Quadrant 3 is over here. And here is quadrant 4. Ordered pairs. So if you have a point on the graph, on the Cartesian coordinate plane, we will call that point, in this case, 2, 3. Because we go on the x-axis, 2 units. We go 3 units on the y-axis. So our coordinate is in alphabetical order, x and then the y. Sometimes we call them ordered pairs, sometimes we call them coordinates, like I just did. You might remember, maybe from Algebra 1, relation is just a relationship between 2 numbers. Just like with your friends, you have lots of different kinds of relationships in the world. You have good friends, your best friends, BFF. You have your boyfriend, girlfriend, you maybe even, you have acquaintances, you have people you know from sports, they're your Facebook friends, all kinds of different relationships with people. Same with numbers, they have different kinds of relationships with each other. Domain. Domain is your input values. Notice in is in both places. Range is your output. To put it simply, we're going to call domain the x values and range the y values. A function, I'm going to deal with that a little bit later here. I've got an entire screen for that. Mapping. Here's what you do for a mapping. You got -3, +1 for that coordinate. This coordinate, -1, 1. This coordinate, 0, 2. This coordinate, 1, 3. If you were to put this into a mapping, you would have 2 circles like so. You would put your domain, your x values, in the one circle, and your range, your y values, in the other one, and we do a little cutesy thing like this. -3, -1, 0, and 1. Then I think just for fun, I'm going to go green. 1 goes over here. I don't need to write 1 again. I've got 2, and I've got a 3. So now, something's not right. How do I have, this is -1, -1. That's my problem. -1, -1. Go back to green. Sorry about that little confusion. All right, -3 maps, hence the name mapping. Doesn't look like a map. There's a picture of something with different things on it. -3 goes with 1. -1 maps to -1. Notice my arrow is going over there. 0 maps to 2. And 1 maps to 3. And that is called a mapping. You don't see it very often, but that's what it is. Vertical line test, we'll come to that in just a moment. All right, all of these things I'm going to talk about shortly, but I want you to write down the words discrete and continuous. Independent variable, dependent variable, and function notation. I think these first 4 are coming with a screen. Function notation, if you could just write f of x, g of x. Here we go. Discrete, a relation when the domain is a set of individual points, hence the graph consists of points that are not connected. Here's what I think, and we might do this in class because I'm cheesy like this. Discrete, jump, 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 discrete, 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 discrete. Continuous, 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 continuous. All right. Continuous is when the domain has an infinite number of elements and the relationship can be graphed with a line or a smooth curve. So they look very different. Discrete, you're hopping around, you gotta jump, 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 jump. It kind of reminds me of staccato in music, for those of you who have that music knowledge. And here we go, this is your legato, your continuous over here. All right, finish what you need to writing on that. Let's move on. Independent and dependent variable. Your independent variable, oh my gosh, it's like x again, isn't it? And your dependent variable is like the y. It's kind of like domain and range. One is going to be graphed on your x-axis. The other will be graphed on the y-axis. That's pretty much all we need to know. Function notation, once again, I've already talked about that really briefly, but f of x is equal to 3x minus 1. And yes, we do say f of x. Weird, but that's the way it's done. All right, don't write this down. This is what's in the book. This is the vertical line test. Here's the Mrs. Talley explanation of anything with a function. I have the birthday test I do when I see points, and I have the vertical line test I do when I see a graph. So this is when I have like a table, like points on, not points on a graph, but like 3, 7, coordinate, ordered pair, right? Vertical line test is what I do when I see a graph. All right, here's what happens. We could do this example in class, which would be perfect. We may still yet. Let's say Joe has his birthday on April 4th. Let's say Jane has her birthday on May 2nd. Billy has his birthday on September 16th. Bailey has her birthday on November 14th. Crazy enough, Sue has her birthday on May 2nd. Whoa, that's crazy. If I were to turn this into a mapping, I would have the people over here. We'd have Joe, we'd have Jane, we would have Billy, we would have Bailey. That's crazy. And then Sue. All right, and then you would have these dates. You would have April 4th. I'm just going to put the numbers. You'll just have to kind of work with me. 16 and then 14, and I'm not going to write the second again. But here's the cool thing. Sue maps to the 2nd. Joe maps to the 4th. Jane maps to the 2nd. Billy goes to the 16th, and Bailey goes to the 14th. This is what I call the birthday test. Does everybody have a birthday? Yes. And it doesn't even matter that over here these people have the same birthday. We know this happens in our class. It happens in our school where people share birthdays. No biggie. Here is when it becomes not a function. So right now what I have here is a function. It all of a sudden becomes a function, and I'm sure some of you have done this at these restaurants where they like sing happy birthday and you get a free piece of cake or something. What happens is some of you are claiming to have a birthday, like Joe might claim he has a birthday on the 4th, and then he tries to say, hey, I have a birthday on the 22nd as well. Now, when I add in that blue, now it's no longer a function. Okay, I wonder if I could undo. Let's see, not a function, now it's a function. Not a function. Because Joe's trying to get away with saying he has 2 birthdays. I know I kids in class are going to say, oh, but what about this, Mrs. Talley, my half birthday? No, no special cases. Joe does not have 2 birthdays. All right. You're going to press pause and write down whatever you need to, because I'm going to clear this out. And we're going to, nope, I don't need to clear it out. Sorry, I'm going to talk about vertical line test. Is that next? Vertical line test basically means my line can pass at most 1 place on the graph. If it passes in 2 places, it's not a function. Okay, kind of going back to this. Everybody can have 1 birthday, we're good. But if you have 2 birthdays, no, not good. All right, here we go. I'm going to see if I can grab this little vertical line. Oh, now, anywhere that I'm looking, I wish I could touch, there's 1, that's 1 intersection. If I keep moving, oh, here we go. Never does this vertical line pass this graph in more than 1 location. So is this a function? Yepper doodles. On to the next one. Does this vertical line, it can touch in 1 spot as I move across, but it cannot touch in 2 places. So far so good. We can have blank, but then we get into here, and what I'm noticing is this touches, whoops, that's supposed to be pen. I'm not on pen. It touches here, and it touches here. So I have a vertical line that's touching in 2 places. So is this a function? Nope. Moving on. You did do this in Algebra 1, but it probably didn't stick too well. You know, it's like one of those things. Okay, as I move it across, we're good. We're good in this territory, but all of a sudden my line comes across and it hits in 2 places. So automatically, not a function. So we're going to call this nope. Bringing my vertical line down over here. Moving it, oops. Okay. Moving it across. Moving this line across. It's only in one spot. We call this, yep, a function. We call this, yep, a function. Yep. Okay, moving on to the next one. Let's see. I'm only in one location. Yay! That means this has passed the vertical line test. Wouldn't it be cool if I could make it so this line here like somehow like exploded or did some weird thing when it would hit two places? Okay, now I have a weird graph right here. This might freak some of you out. Look at this graph. You're like, yeah, it's good, Mrs. Talley, it's good. It's even good right there because I'm passing through one location right there. Okay, I'm going to keep moving. Okay, some of you are going to think, hey, 2 spots, what happened? No, it's not. This one is an open circle, so it's not including that point. So we're good up to this point, and then this one kicks in. This is called a step function. It's actually in this chapter, but I don't see it in the standards. Okay. All right, so this actually passes the vertical line test. So I have a lot of yeses on this one, don't I? So this is another yep. That's a function. It's called, obviously, the name, step function. It looks like stair steps going up. All right, here we go. I have lots of examples too, you guys. State the domain and the range of the relation. All right, I don't know how much of this we want to do. The domain, we can just put D, or you could do the mapping with the circles. I'm going to say -4, all my x values. -3 would be another x value. 0, 1, and 3. All I did was copy down my x values. Okay, my range, I'm going to put an R, and we're going to list out all the range numbers. 0, 1, -2, 2, 3. Okay, got my domain and a range. Is this a function? The easiest way, I think, when you've got a graph, go with the vertical line test. And let me see. Got my vertical line hanging out over here. Use me. I think we're good. We're good. We're good. We're good. The line only passes through 1 point at a time, and it never passes through 2 points at a time. So we are golden on this. So is it a function? Yes. Example 2, state the domain and the range. I'm actually going to skip that. I don't even think that you need to practice it one more time. Is this a function? You can check with your points. Does it pass the birthday test? But since it's already in picture form, it's easiest, I think, oops, that's not what I'm going to do. I think it's easiest for us, once we've got it in a graph, it's just easiest to do the vertical line test. 1 point, 1 point, 1 point. Lovely. Is this a function? Yes. Example 3. I could have you graph this out, but I thought I would get a graph already ready for you. The table shows the average fuel efficiency in miles per gallon for light trucks for several years. Graph this information to determine whether it represents a function. Is it discrete or continuous? Okay, well, you can do the birthday test if you're looking at this. And it looks like all of these 2001, all these numbers here only have one value with them. It's not like we're saying 1998 again here and trying to give it a different number like 20.8. All right, and because this passes the birthday test, it is a function. So yes. Okay, is it discrete or is it continuous? Dot, 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 dot. Think of a frog jumping around on lily pads. Is that discrete? You betcha it is. So this is what we call a discrete graph. Okay? Look at this one. The table shows the average weight of a baby for several months during the first year. Just determine, I don't want you to graph it. We're just looking at the table. Does it represent a function? It looks like 1 is mapped to 12.5, 2 matches 16, 4 to 22, 6 to 24, 9 to 25, 12 to 26. All right, I don't see any number over here in my domain that is assigned to different numbers in the range. Okay, so yes, right now it is a function. I put FC in sometimes to abbreviate that. If you were to say 1 matches 15, then it would not be a function. All right, there's also this in this section here. They want you to graph the relation represented by y equals 3x minus 1. Okay, find the domain and range, determine if it's a function, to state whether it's discrete or continuous. Woo, that's a lot. First of all, how do we graph y equals 3x minus 1? And from now until the end of time, if you don't know how to graph, you can always go back to the table of values. And what do I like to do with my table of values? I like to start with my fave 5. Negative 2, negative 1, 0, 1, and 2. I call them our fave 5. All right? That means you put negative 2 into the equation. So 3 times negative 2, negative 6. And negative 6 minus 1 is negative 7. Then I put negative 1 in for x. Negative 1 times 3, negative 3. Minus 1 is negative 4. That's what my y value comes out to be. 0. 0 times 3 is 0. Then we got negative 1. If we're really on the ball here, we can see a pattern. This is plus 3, plus 3. If we add another 3 to it, we come out at 2. Add another 3, you come up to 5. Or you can just put 2 into the equation. 2 times 3 is 6. 6 minus 1 is 5. The cool thing is, if you remember your algebra really, really, really well, and I mean really well, this is your y-intercept. It's the number across from 0 on your graph, or on your table. And this is your slope, which means that's your rate of change. Every time you go up 1 over here, you're going up 3 over here. Okay, that's a lot of information. That's a whole lot of a couple chapters in Algebra 1, basically. Let's graph this puppy. Negative 2, negative 7. 1, 2, 3, 4, 5, 6, 7. Oh, it's off the graph. Negative 1, negative 4. We get it. It's right about there. 0, negative 1. 1, 2, and 2, 5. Now, here's the kicker. It looks discrete, doesn't it? It looks awfully discrete. We're popping from lily pad to lily pad to lily pad. The thing we have to remember is we just chose 5 points. Could somebody else come in and say, I want to check negative 1.99999 repeating? Oh, yeah, they could. And somebody else could go in with negative 1.98. And somebody else could go with negative 1.97. And you're like, why would I want to do that? Somebody might want to do that. And that's the case, then you have all these points in here too. You've got, oh, I guess they're down here. All of these points are in there. And if we were to graph this, just like you did in Algebra 1, do you remember doing this? Now it doesn't look quite so discrete. We're not taking exact points and saying that's it. We're making a line through these points because this is also a solution to this equation. So much information. So, the domain. Let's go back to the questions here. We graphed it. Done. Find the domain. I'm not going to write it out separately. I just want you to make a note somehow. This is your domain. We're going to put D. These are your range points or your range values. So you're going to put R for that. On a quiz or a test and most of your homework, you're going to write it out. All right? Then determine whether the equation is a function. Well, vertical line test will work. If you look over here, it also passes the birthday test. So yes, it is a function. And is it discrete or continuous? We're not hopping from lily pad to lily pad. All these points are a part of the graph. So this is what we call continuous. That's a lot, isn't it? Example 6, let's try it again. Different kind of graph. Y equals 2x squared. Once again, the fave 5 will work. I like it best, however, if we have just an idea of what kind of graph this is going to be. You see x squared, you should be thinking, oh yeah, a parabola. I should see a U-shaped graph. If you don't have enough points to see that U-shaped graph, keep adding on to your fave 5. All right? Oh, I think I'm supposed to have all those questions. We'll talk about them here. Negative 2. Negative 2 becomes squared first. So that's 4. 4 times 2 is 8. Negative 1 squared is 1. 1 times 2 is 2. 0 times 2 is 0. 1. Oh, there's also a symmetry. If you recall, like these match up. These will match up. Okay, you have to be careful, though. That only works if you know this is your vertex. Let me graph. Negative 2, 8. I'm going to go off the thing. I know it's a little weird, but I'm going to do it. Negative 1, 2, 0, 0, 1, 2, and 2, 8. And remember, all of these points are solutions to this equation. So, quick review. This is your domain. That's my D. These numbers are your range. Is it a function? The birthday test passes, the vertical line passes, so yes, it's a function. Is this discrete or continuous? Well, it's continuous. I'm going to abbreviate that. Let's move on. All right, here's our function notation. So here's a whole other idea which you did not do hardly any of when you were in Algebra 1, just maybe like a day that you spent on it. Notice how it has f of x. This is meaning, hey, you know what the relationship between this number is? Between these numbers? It's actually a function. That is what it's saying. We actually have a function. Instead of saying y equals, we just know that when it says y equals or t equals or m equals, that is just some kind of a relationship. But once we put this function notation, we are saying, by golly, this is a function. It passes the vertical line test, and it passes the birthday test. Now, when you see this x cubed minus 3 written out, they're going to have you find something else. F of negative 2. That means you get to put negative 2 in place of x. Or they already did there. Now you get to put it in here. So I'm going to write it out like this. F of negative 2 equals, instead of x, you're going to write negative 2 cubed minus 3. This should look like what you did in chapter 1 when they said evaluate, and then they had a whole thing like this, and then they would say let x equal negative 2. This is basically code for what you just did in chapter 1. The only difference is it's a fancy notation. So we're going to be fancy schmancy. I think there's a book for kids out there called Fancy Nancy. This is the Fancy Nancy version of doing what you did last chapter. It's just saying, hey guys, we're working with functions now. We're fancy. Fancy functions. I should write a book about fancy functions for math with the Fancy Nancy theme. Negative 2 to the third power is negative 8. And then I have minus 3. Notice how I keep writing this f of negative 2. I want you to do that because this is, once again, if we're going fancy pants, we got to go the whole way. Negative 8 minus 3 is negative 11. This is your answer. F of negative 2 is negative 11. Let's try another one. Uh-oh. Oh, this is different because now instead of substituting whatever we did last one, now we're going to substitute in 2t. So I'm going to rewrite this. F of 2t equals 2t cubed minus 3. All that happened was what was here is now a 2t instead of x. I'm going to keep writing this out. F of 2t, like I'm going to have you do on your homework, 2t cubed is actually 2t times 2t times 2t. 2 times 2 times 2 is 8. T times t times t is t cubed. And then minus 3. If I could simplify further, I would, but there is no other math I can do with this. I'm done. This is my answer. F of x equals x squared plus 5. This time, you're putting negative 1 into the problem. So we have f of negative 1 equals negative 1 squared plus 5. I keep going. Keep writing this out. Negative 1 squared is 1. 1 plus 5 is 6. And that's your answer. F of negative 1 equals 6. Basically, this also means, too, just another thought, if you were to graph this, if you were to go on the x-axis to negative 1, your y value would be 6. All right, this is example 10. I'm going to let you try it and see what you come back with, and we'll just kind of double check that. You're on your own on number 10, And that's the end of a very long and very informative lesson.